сейчас хватит?
Не знаю.
Да.
Я буду надеяться на это.
Надеяться, да.
Ну, если что, я там, может быть, твой возьму.
Мы тоже, хотя не очень.
Нет? Нет, ну тебе обычно его хватало.
Сейчас хватит.
Да, сейчас.
У тебя наушники есть? Или тебе не нужны?
Так, а зачем мне наушники?
Они нужны, чтобы говорить.
Подожди, а почему я не могу просто в телефон говорить?
Нет, ну просто тебе нужно одной рукой держать телефон.
Да, я понял тебя, но у меня, по-моему... Нет, наушники у меня есть, но они чтобы только слышать, а не чтобы говорить. Сейчас, подожди, я посмотрю. Ну, может быть, у меня есть... У тебя не iPhone?
Нет, у меня другой. У меня
Нет, да, что-то я не учел этого обстоятельства совсем, к сожалению. Это у меня наушники, но они к айфону не подходят, к сожалению. Вот там у него специальное гнездо. Ладно, мне придется говорить какое-то время в микрофон. Вот. Просто по-другому не получится, к сожалению. И я надеюсь, что зарядки моего телефона хватит надолго. Так. Видно, да? Нет, я, конечно, по-английски пройду. Okay, I'll continue. I'm sorry for this late beginning. Unfortunately, Moscow is a very big city, and I can't win time this time. Well, but since Professor Г.И.Шарыгин discussed something about the Jacobian Conjecture and the corresponding Dychmear Conjecture. Have you said something about the... No. Okay, then I'll...
You said that there is a relation between...
Yeah, okay. Then using this possibility, since he began to speak about that, I'll tell about these conjectures more in more detail. Right.
Turn off the microphone over here, because there will be echo.
Ah.
Yeah.
Okay. Now it's okay? Okay. Then let me continue this line, and I will talk about the Jacobian conjectures and the Dychmear conjectures, and then I will discuss certain problems related to construction and classification of commuting differential operators and their relations to the problems mentioned above. I mean the problems about deformation, quantization, etc. So first of all, let me point out that these conjectures, this Jacobian conjecture says that if you have a polynomial map between say Cn to Cn with non-degenerate or just with constant Jacobian, then this conjecture asks whether there is an inverse map given by polynomials. Up to now, these conjectures are still open, and this is well-known open conjectures. I'd like to say that these are conjectures. So these are conjectures for solution of which a big prize will be earned. Because this conjecture was posed by Keller in 1930s, I think, and after that, many mathematicians tried to give a solution, and there were many wrong solutions, many attempts to resolve this conjecture, and up to now, all attempts failed. Moreover, Now there are two classes of mathematicians. One class believes that this conjecture is true, and another class believes that this conjecture is wrong. Some mathematicians think that this is probably is true for n is equal to 2 and is wrong for n greater than 2, but up to now no solution is found. Right. For example, Igor Rostislavich-Shafarevich believed that this is true for n is equal to 2 and it is wrong for n greater than 2. Stepan Arevkov, who now is working at Steklov Institute, believes that this conjecture is wrong, and he always tries to construct a counter example. But up to now, no answer is found. Well, but this conjecture is closely related to another open conjecture, which is called the Dychmear Conjecture. More precisely, this is a series. There is a series of conjectures. Let me call this Jacobian Conjecture by such abbreviation, GCN. GCN, this is a Jacobian Conjecture for C power n. And another conjectures posed by Dychmear. These conjectures were written in his seminal paper of 1968, where he solved a very beautiful mathematical problem. Namely, he described the automorphism group of the first Weyl algebra. Let me fix a notation. So George denoted the algebras by the big capital W, but I will denote them by big A n. So this is nth Weyl algebra. So namely, this is a standard notation accepted by algebraists. This is an algebra of differential operators with polynomial coefficients. So this is just the same algebra as was introduced before, and which was used by Fedosov in his Fedosov's quantization construction. But we assume here only that K is any field of characteristic 0. So actually, the Jacobian conjecture can be also formulated for, say, any field of characteristic 0, not only for C. But for convenience, you can think that K is equal to C. Doesn't matter. Well, this is called the nth Weyl algebra. And the Dychmear conjecture is very simple. It's very clearly and easy formulated. Let me denote this set of conjectures by DCN, the Dychmear conjectures. They said that they asked whether any non-zero endomorphism of this field algebra is equal to an automorphism of this field algebra. Very simple question. Well, in his paper by 68, Dychmear described quite explicitly in terms of generators the automorphism group of the first wave algebra. In his seminal paper of 1968. And this was question posed as problem number 6 in his article. And since then, some mathematicians tried to resolve this question, but also without any success. So in the beginning of our century, the beginning of is what it was established that these two series of conjectures are equivalent. More precisely, it was proved that they are stably equivalent to each other. This was done by Tsushimoto. Probably you know him. He was a Japanese mathematician. And independently, and a little bit later, by Kontsevich and Kanel-Belov. So there are two independent articles. The beginning of our century, the 21st century, beginning of 2000, so 2000, 2010. Yeah. So I remember Kontsevich gave a talk at MPM in Bonn in 2005 about this paper with Kanel-Belov about this equivalence of two conjectures. But when they wrote this paper, they didn't know that Tsushimoto already made it a little bit earlier. So there were two papers for Tsushimoto before them. And they proved that these conjectures are equivalent in the following sense. So from so it follows that from DCN it follows GCN, but in converse direction we have that from GC2N follows DCN. And so they call this equivalence by stable equivalence. So these conjectures are stably equivalent in the sense that that we have the following implications. So if we know the Dychmear conjecture for n-field algebra, then we can prove the Jacobian conjecture for Cn. And if we can prove the Jacobian conjecture for GC2n, then we can prove the Dychmear conjecture for DCn. So in such a way, you see that we have now two series of very strong open conjectures. In this series of implications, there is one case, one separate case, it is not covered. Namely, the conjecture DC1, namely the conjecture for the first wave algebra, is open, but the Jacobian conjecture for n is equal to 1 is trivial, so that's not interesting at all. And therefore, we cannot derive from this DC1 conjecture anything interesting. But nevertheless, certain algebraists believe that if we could prove the Dychmear conjecture for the first algebra, first value algebra, then we could derive from this the conjecture for the second value algebra, and then therefore we can prove the Jacobian conjecture for n is equal to 2. Maybe it is true, maybe not. Nobody knows up to now. But nevertheless, DC1 is also open.
We said that Dychmear described automorphisms of A1.
Yes, yes. Automorphisms are described. They are very easy in a sense. They are tame. But it's not known whether the endomorphisms coincide with automorphisms. This is a very strong problem. Well, this is certain motivation to study differential operators inside the real algebra. And as we'll later mention, there is another conjecture due to Yuri Berest, which is related to this Dychmear conjecture. Namely, it's stronger, but it was formulated only for the first value algebra. Later, I will formulate this conjecture. But nevertheless, this is just a remark which serves as a highlight for our problems which we will consider in this seminar. By studying differential operators, or commuting differential operators, or rings of commuting differential operators, we will certainly meet a certain type of questions related to these famous open conjectures. I will say even more. To prove the Jacobian conjecture for Cn, it's enough to prove that any endomorphism of the first of the nth value algebra preserving the usual filtration given by the order function of differential operator is an automorphism. So it's enough to prove that any order preserving endomorphism of the nth value algebra is an automorphism to prove the Jacobian conjecture. So it's an important remark. Prove the implication in DCN. That's enough. That any endomorphism that preserves, but not zero endomorphism that preserves order filtration. Is an automorphism.
Excuse me.
Yeah.
Could you explain the order filtration again?
I mean the following easy observation. For any ring of differential operators, or for example, for algebra, the order or the degree of a differential operator is just the sum well, if P is equal to sum A I dI, the sum is finite, and di here means, as before in the talk of G.И.Шарыгин.
So is it just an element of divided algebra?
Yes, P is an element. So I try to define the order. That's the usual degree. Somebody called this order the degree function. I will call this order the order function. If you have just a polynomial differential operator with coefficients in this polynomial ring, then the order of P is just the maximum number between all these terms, where I means just the sum of indices in this multi-index, the usual notation. It's just the usual order of an operator with respect to d1, dn. Well, but well, all these conjectures are very difficult. And of course, we can think of these conjectures only just a hint that the problems which you'll consider here are important for the mathematics, particularly because they are connected with these deep problems. I don't think that we will be able to solve them, but we can always think about them when we deal with differential operators. Well, then now I'm going to continue with my notes, and I want to discuss certain questions corresponding to the previous talks by George. And I want to consider now certain differential operators, not necessarily on a manifold, and I will be interested in commuting families of such differential operators. Such commuting families were called by some authors, like by Belinson, Lechenkov, and Gates-Gorey, as quantum integral systems. And now I will talk about them a little bit. I'll introduce notations and pose certain problems related to this, to the existence and construction of commuting families of differential operators. So, so there is the following analogy offered by these guys, which I mentioned before, Braverman, Lechenkov, and Gates-Gorey. So first of all, let me recall what we mean here by the classical integrable Hamiltonian system on a manifold. George already told us about this, but nevertheless, let me remind that the classical integrable system on a manifold X of dimension n. This is just simply a set I1, In of functions on the cotangent bundle on X, which Poisson commute with each other with respect to the standard Poisson bracket that I already know about that, and George already discussed this many times before. Moreover, we usually assume that I1 and In are functionally independent. Now, one of problems of deformation quantization, and I hope that later George or maybe Yasushi will make a talk about them, is how to quantize this Poisson commuting sub-algebras. And in particular in this situation, if we will try to quantize this Poisson commuting families of functions, we should obtain commuting differential operators. And therefore we have the following analogy, algebraic analogy. Of this picture. We will call we consider a pair lambda and f. Lambda is an irreducible affine variety. Also of dimension n. So, just for the general situation. This is the analog. Oops. Well, I forgot to add here that we have the dominant morphism. That means that just the image is dense and lambda. With Lagrangian fibers.
So what is that?
Well, let's take this some reducible affine variety. So usually this is a moment map. So we just can take just something like Rn or
So
Cn.
you're now trying to formulate a
Yes. No, but yeah. I just forgot to add this line, this classical picture. So if you have a classical integrable system, then we have the moment map given by these functions. And this is a dominant morphism with Lagrangian fibers.
What is the definition of dominant morphism?
This means that the image is dense.
What is lambda?
Well, in usual picture, lambda is just Cn or Rn, if you like. This is a fine variety.
It's strange.
Why? Well, we have n. This is n, we have n functions which give us this map.
Yeah, but this map cannot have compact image.
But why we need compactness? It's dense, but nothing more.
Yeah, but dense is it always the case, and they just don't know this about the classical integrable system. Is it always the case that the map, momentum map is dense? Because I have some impression that in some cases the momentum map can be compact, can have compact image, and that means that it cannot be dense in Rn.
No. I mean, here it is dense because these functions are functionally independent in a sense that they give us open map, at least locally open.
I mean, they are globally functionally independent on all x.
On all x, yes.
That means they have. But can you give an example? Just to make it look a little bit more closer.
I think the best example is this generalization to quantum case.
Because I never thought about this map as momentum map as being compact, as being dense. I have an idea, and I know there is this famous Abort theorem, which says that the image of momentum map is a convex body, and convex body is not dense in Rn. So this.
Yes. If you consider if you consider if you consider compact variety, then it will become of course okay. What means the dominant is about what dominant comes here from algebraic geometry. In algebraic geometry, there are no restricted sets. They are if they are open, so if they contain an open ball, then it will be automatically dense. That in this sense it's considered. So we consider now this map given by in this picture. Let me erase this word dominant. Yes, you are right. It's not a dominant. Just a moment map. Yeah. Well, just because I want to consider algebraic analog of this picture, nothing more, and I don't want to say anything more. But algebraic analog of this picture is when we replace this lambda and this moment made by then any affine irreducible variety, and then consider instead of this moment map. This is an analog. Of the target and the moment map. Now take the ring of differential operators. smooth the algebraic variety.
I'm being sorry. In the definition of algebraic integrable system, we have an irreducible affine variety, right, of dimension n.
Yes.
And F, what is F?
Wait, I will write it just now. And then F, or more precisely, F star, is a map from the homomorphism from the algebra of regular functions on lambda to d of x. And d of x is a quantum analog of this Poisson algebra. This algebra of functions on the on T star x. Well, what is F star? This is it is an analog of this map, but written in algebraic case. So if x is algebraic and lambda is algebraic, just say an, then and I1, In are polynomials, then this is just an algebraic map, and therefore it induces homomorphism of regular functions. And now we consider as an analog of this F, this map F star, and automatically this gives us, in the sense of geometry.
What is again F?
F is just homomorphism.
So F star is a homomorphism.
Right.
What is F? Oh, so you already raised it.
Yes, because what is F star? F star is a map induced on functions by this geometric map F. So, well, if these two rings of functions were commutative, then any F star will induce a morphism of algebraic varieties, right? Mm-hmm. But now, in non-commutative sense, what is F? There is no clear answer on this question, right? And therefore, we replace this moment map by just an algebraic homomorphism, by an algebraic map from the ring of regular functions on lambda to the ring of non-commutative functions, the quantum analog of the Poisson algebra of functions on the T star x. This ring is now non-commutative, and as you told us before, we can think about this ring of differential operators on manifold X as a quantization, right? Mm-hmm. And now we replace the moment made by this map F star. It's a homomorphism of algebras, of sheaf of algebras, if you like. Okay. And now I can give a definition of this quantum system. Let me write it before. So now quantum completely integrable system or simply QCIS is just a pair lambda and theta, or say F star, or F star which is just a homomorphism is an embedding. Well, this is a definition due to Berger-Mann-Nittinghoff and Gates-Cohen. This is an algebraic analog of this classical picture. Now we know that since we take a dimensional affine variety, then its field of algebraic functions has transcendence degree n. If lambda is just an as before, then this ring is just a ring of polynomials. And the image of this ring will give us n, will give us a ring generated by n commuting differential operators. So in the sense of this definition, any quantum completely integrable system is just a subring of commuting differential operators on some manifold X. And in a sense, we can think about this ring as a quantization of certain classical integrable systems, because there is a clear analogy. So if we take here at this moment map, the map f star from functions on lambda to functions on OT star x, then this will be a classical analog of this map of algebras. Nothing more. And then the following question appear. The first question is how to construct explicitly these quantum integrable systems. It's a natural question because they are related to the classical question. And second question could be classify somehow this quantum integrable systems or not. It's a difficult. Both questions are difficult and both questions are open. And these are two fundamental problems: how to find an example of quantum completely integrable system, and how to classify them. Of course, these problems are also very difficult in any case. But in a sense, this problem of classification of quantum completely integrable systems appears to be a little bit, maybe even easier than this classical case. And now I want to explain why. Namely, let me formulate a certain results in this direction, known for the ring of differential operators in dimension 1. This is the case where the answer on both questions are very well known. Well, they are not completed, of course, to the end, but we know a lot of information about such quantum integrable systems. Well, let me assume that n is equal to 1. And now let me consider the following formal situation. First of all, let me observe that in this general picture, we can take instead of x, instead of some variety or manifold, certain formal objects. Namely, we can replace x by a formal neighborhood of certain smooth point. The first mysterious effect which appears here, there's a problem of classification of these quantum integrable systems, is that even if we replace x by some formal or very small neighborhood of a point on variety x, then we will not lose any information. Moreover, the task will become easier in a sense. So let's consider a formal neighborhood of a point Then this ring D of x, so I replace x by this formal neighborhood. Well, let me write this here. Will be just equal to the following object: k of x1 xn d1 dn. Well, if n is equal to 1, then this is just equal to the ring k of x of d. So this case is much more simple than usual case. In general case, if you take a point on a smooth n-dimensional variety, then any function, since we consider everything smooth, algebraic, any function, well, k we can assume to be equal to the field of complex numbers, and any function is can be decomposed into its Taylor series. And then the ring of germs of all such functions in this small neighborhood is just this ring of formal power series in x1, xn, in coordinate function. And d1, dn is just a standard vector fields with respect to this coordinate system, or in algebraic sense, these are just derivations of this ring with respect to this variables x1 and xn, right? So by replacing x by its formal neighborhood, we come to a formally algebraic ring, which can be considered just in very general algebraic sense. And in this very general algebraic sense, we can take the ground field to be equal to any field of characteristic 0, not necessarily the field of reals or complex numbers. We can take k to be equal to q, for example. Well, and now in this case, the following question appears. Question 1. Can we classify these quantum completely integrable systems even for n is equal to 1? And Q2, can we produce a way to construct
classify quantum completely integrable systems on this neighborhood?
Yes. So can we classify these quantum completely integrable systems? Now can be reformulated as a question: can we classify all commutative subrings in the ring of differential operators? Because any quantum completely integrable system by definition is a pair. Now if you take any commutative ring of dimension 1, gives us some fine algebraic variety. Of course, it must be without zero divisors, because we assume that the affine variety is reducible. So this is a good, for any good commutative ring, I mean the ring of dimension 1, which means that the field of fractions of this ring must exist, and therefore this ring does not have any zero divisors. Second, the field of fractions must be of transcendence degree 1. And the ring must be finitely generated. We can assume that in any way. But in fact, for the case n is equal to 1, it will be always true. For any such ring, this embedding gives us the same commutative subring here. And the first question can be rephrased as how to classify all commutative subrings in a ring of differential operators, which we can take as this ring. Note that we practically don't lose any information. So if we try to find commuting differential operators in the whole manifold X, then obviously we can embed this commuting family into this ring, right? By considering the germs of functions, germs of coefficients. In particular, if we will be able to solve this problem in this ring, then in particular we will be able to solve the problem in this global situation. And I'd like to say that one of main points of this theory in dimension 1, which is very well known, is that in fact it is possible, and by considering such local ring of differential operators, purely algebraic ring of differential operators, we don't lose any information. Any reasonable quantum integrable systems, and these are so-called algebraically integrable systems, and later I will explain what does this mean, produce commutative families of operators with algebraic functions as coefficients. And therefore they are defined on certain global algebraic variety. And the second question, can we produce a way to construct explicit examples? Of Q, CIS. For n is equal to 1, the answer is well known, and this is a rich theory which was developed since 70s or even earlier. It was started by famous algebraists like Isaiah Schur, Wallenberg, Isaiah Schur, and Bertrand Chaudy in 20s. In the beginning of 20th century, and then later it was rediscovered and developed by this Novikov school, in particular by Igor Krychev and by many famous algebraic geometers like Mumford, Drinfeld, Dychmear too, Dychmear, Verdier, and so on. So many mathematicians were involved in this activity. So in this case, the answer is yes. For Q1, answer to Q1 is yes. And namely, there is algebraic geometric classification. Algebraic geometric terms. For A2, the answer is yes, and in good cases, but not always, but in good cases, there are explicit formulae. Well, but to explain these two answers, I will need a lot of time, of course. So I don't know. So if the people will be interested, we could explain certain parts of these answers but in fact I need at least half of a year to explain everything behind this classification theory. But let me only mention here two important things. So first of all, let me introduce the notion of rank of this quantum complete integral system in this case. So in this case, we have the following picture. So I recall that QCIS is just a map from all lambda to this ring D, which I assume to be equal to this ring. And let me denote by B the image of this map. And so I will just replace this pair by the unique ring B, by the image of this ring. Obviously, if you have any commutative subring here, then we can produce of this ring a certain algebraic variety and then obtain this embedding F star. So first, let me mention general properties of this ring, general algebraic properties. Where B can be considered as any commutative subring in this D, in general commutative subring in D. So first of all, B is integral, which is obvious because the ring D itself doesn't have any zero divisors. Since B is integral, we can consider its field of fractions. Then the transcendence degree of this field of fractions is equal to 1. Well, and at last, it can be proved that B is even finitely generated. Okay. So in particular, from this property, it immediately follows that there is an irreducible affine algebra. No zero divisors.
Oh.
It's a domain.
But that's just a condition, or
It's
a property for any?
It's a property for any commutative subring in D. Why? Let me explain this briefly. Because D doesn't have any zero divisors. You showed us before how to multiply two differential operators, right? And we multiply two differential operators. We should look at their highest symbols, right?
Yeah.
But when we consider the coefficients in this commutative subring, the product of any functions, of any two non-zero functions, is a non-zero function, right? Therefore, the ring D does not contain any zero divisors itself. And by this reason, any subring of D will also be integral, right? Any subring will not contain any zero divisors. Well, since it's integral, so it doesn't contain any zero divisor, it's commutative by assumption, then we can consider the field of fractions, which I denote by quote P. The field of fractions of this commutative subring has the property that it has transcendence degree 1. That means that it has one transcendental generator, and then this field is an algebraic extension of a purely transcendental field K of T. What V contains K of T, the ring of ring of rational functions in one variables, and this extension is algebraic. It can be proved. Well, this is just a list of properties that could be proved, but of course it should be done. It will take some time. It's not so easy. Well, if you like, we can discuss it in detail. If you can believe me, then just yes. Yes. Right. And by the way, I am sorry because the beginning of my talk was a little bit not clear because I'm not very well prepared for this talk because you told me about this illness of Pavel just on Sunday evening. I had no time to prepare something. Yes. Well, I am going just to explain certain deep problems, certain global questions which appear behind all topics in our seminar, because these quantum integrable systems are related to your problem of deformation quantization, in particular because I hope you will explain us how to deform the commutative Poisson algebras in universal algebras. The ring of differential operators and commutative subring of differential operators are interesting because not only because they are connected to the problem of deformation quantization, but also because they are connected to these deep open conjectures like Dychmear Conjecture or Jacobian Conjecture.
So the fact that B is finitely generated over K is again an assumption?
No, it is a correlate, it is properties. These are facts.
So
or any commutative subalgebra.
The fact that B is finitely generated over K.
For n is equal to 1, it is a property of any commutative subring in D.
Does it follow from the first two properties?
Well, formally not, but it also can be proved. If the transcendence degree is less or equal to 1, less or equal to 1 because we can take a trivial subring consisting of constant, right? Then transcendence degree will be 0. Then let me correct this sign. But it can be proved. For n is equal to 1, it can be proved. It's certain algebraic.
So it doesn't follow from the first two?
No. Because, for example, in n is equal to 2 or greater, then these two properties will still hold, namely B will be integral, and the transcendence degree will be less or equal to n, where n is a dimension of our variety. But B will not be necessarily finitely generated. But for n is equal to 1, this is true. This is an algebraic property of any subring. And by this reason, we can just consider a general problem of classification of commutative subrings inside this ring.
So any such subring has the form F star of O.
Exactly.
And this is
exactly. It's just I'd like to write here. And therefore, there exists an affine variety as before, such that B is isomorphic to O of lambda, and therefore B is equal to F star of O of lambda. Well. Good. Then, rank. What is the rank? Now let's consider such a ring B, and I will introduce two notions of rank. the first notion of rank, the first definition of rank. This so-called algebraic rank. This rank was first introduced by Drinfeld in his short paper according to this theme. And later was more clearly formulated by Wilson, George Wilson. So the rank of B in this algebraic sense is just a great common divisor of all orders and second, what is the rank? The rank of B is the dimension of the following space, dimension of space of functions psi, which are common eigenfunctions for all commuting operators from B. Here, phi, or phi, and generic point. Of lambda. So let me recall by the Hilbert's Nullstellensatz, this affine variety lambda defined by this commutative subring B is a variety consisting of prime ideals of B, or the closed point are maximal ideals of B. And any maximal ideal defines a character high.
Those are two equivalent definitions.
Yes, yes, yes. So geometric definition says that the rank of B is a dimension of this space of common eigenfunctions of all operators from B at generic point high. At generic point high. This is important, that the point must be a generic point. Because often it can happen that at certain points this dimension jumps. But at generic points are high. Of course, both definitions are equivalent. But I don't know which one you will prefer. This is a purely algebraic definition, but it doesn't say anything about the solutions of differential equations. This is more geometric or more analytic in a sense, because from this definition we know that all these commutative operators have a big space of common eigenfunctions, and its dimension is called rank. And in fact, these common eigenfunctions, which are traditionally called Baker-Heezer functions, could be written quite explicitly in the case if the rank is equal to 1. So, and now, well, now the rank is clarified in this case. Now, if this rank is equal to 1, then this quiz QCIS is called algebraically integrable. So in this case, on the case of algebraically integrable systems of dimension 1, so in this case, when rank of B is equal to 1, there are quite explicit formulae. Due to Krichyver, of this generator of this subspace, of the spaces of psi. And therefore, there are quite explicit formulae of families of commuting differential operators. Examples of commuting operators. Also, in these cases, Becker-Hazer functions lead to quite explicit solutions of famous, very well-known nonlinear partial differential equations like KdV, Kp, and so on. These solutions are so-called algebraic geometric solutions, which came from this theory of commuting operators. Well.
Yeah. Very far behind the schedule.
Ah, right.
It's almost 7:30.
Right. But it is because I was late for almost half past.
It's not as late as it
Yes.
is.
I see.
These clocks
I
are
see.
15 minutes in advance.
Maybe I just want to say one remark about the Weyl algebra, just to point out the relation of all this theory with the question from the beginning of this seminar. So obviously, this ring D, which we consider now, just a ring of formal neighborhood of a point on a smooth right X, obviously contains the first Weyl algebra, right? Because polynomials are inside of the ring of formal power series. And now, the good question is how to classify all commutative subalgebras in A1. We have a general classification of commutative subalgebras in D, but how to restrict this classification to A1? This question is in a sense open. So there are no good way to restrict this classification to the classification of commutative subrings in Weyl algebra. But in this case, there is another conjecture. It's called Bayes' conjecture, which is is in a sense stronger than the Dychmear conjecture, which says the following thing. So let me write down this conjecture. So, assume that we have a polynomial in two variables, some generic polynomial. Generic polynomial. and another interval. And assume that we found some operators PQ from the first algebra such that f of PQ is equal to 0. So assume that we have found certain solution of this polynomial equation in the first field algebra. Then it will be checked that P and Q commute. So solution of any of this polynomial equation is a pair of commuting operators. And he asks the following interesting question. So obviously, if we will apply any automorphism to this pair, so for any automorphism of the first array algebra A out A1, the pair phi of P, phi of Q is also a solution of this equation. Right? That's clear. Now consider the orbit space. The conjectures now ask. Is it true that if the genus of the curve given by this equation, so each equation in two variables gives us a plain algebraic curve, right?
The conclusion that P and Q commute follows from the.
Yes.
So this is the conjecture.
It's not conjecture; it's a conclusion. If
It's
P.
always the case.
Yes.
So very polynomial.
Generic polynomial. Well, but I think that it's always true for any polynomial, and it's interesting task for students. I'm waiting for students. One of my questions to students to prove it for generic polynomial. This conclusion for any polynomial. Sorry, that this conclusion is true.
For any polynomial.
For any.
Is it solved?
Hmm?
Is it conjecture?
No, this is an exercise or small problem which I offer to the students.
And it's not open. It's
Well, I think it is true. Well, I haven't tried the proof, but I believe it's true. I believe it's true. I have certain ideas how to prove it, but I'm waiting for a student who will resolve this exercise.
F is any polynomial.
No, generic.
In the conjecture, it's a generic polynomial, but I believe this is true for any polynomial.
So it is proved. So if you have a generic polynomial, then this is true. This is something which Alexander research says can be proved easily.
Well, not easily, but well, it can be proved.
But if f is any polynomial, non-generic, that is to say, can be not how to call this, decomposable, can be.
Yeah.
Can have some
Well,
linear relation.
any is any.
Yeah. Then it is also true, but
Yeah.
the proof is not.
Yeah.
Taken.
Well, I don't think that's a deep problem, but just a good problem for students, for PhD students who start to deal with these things.
What does generic mean?
Generic, well, if you like, that means that this set of coefficients is generic. Or in other way, you can assume that the curve given by this equation is smooth. Then the conjecture asks if the genus of this curve is greater than 1, then the set of orbits orbits of solutions of pairs PQ such that f of PQ is equal to 0 is finite. And if j is equal to 1, then it is infinite. This is an analog of the famous Mordell conjecture from number theory, if you notice that. The Mordell conjecture states something about rational points. Mordell conjecture. Mordell conjecture says about rational points on curves, right? And this is a non-commutative analog of this Mordell conjecture. But it's funny that from this Bayes conjecture, so if it is true, if Bayes conjecture is true for some curve,
what must be, sorry,
yeah,
what must be in the range of 1?
genus.
Genus.
For if this Bayes conjecture is true for genus greater than 1, at least for one curve, then we could imply the Dychmear conjecture for the first algebra. So in the sense, that non-commutative Mordell conjecture is stronger than the Dychmear conjecture for the first real algebra. Therefore, it's quite interesting to study these orbits with respect to the automorphism group of the first real algebra of commuting pairs of operators. So you see that this theory of commuting operators can help us understand Dychmear conjecture. Of course, it's very difficult. There are several statements about commutative subrings in the first real algebra. These results are quite interesting and non-trivial. And the last result in this direction was published by Makar Limanov in the beginning of this year. Very interesting article.
So what is this conjecture? It said for orbits of pairs
It's finite, right?
it is written if finite.
Is. Sorry, that's a misprint. Is. Yeah. One letter, but the sense is completely changed.
So the number of orbits on the direction of all the
Yes. Well, genus 0 is not interesting. Genus 0 means that this algebra generated by one polynomial, the statements is practically empty. It's not interesting case. The most interesting questions appear here exactly in the case when two commuting operators satisfy a non-trivial equation in the sense that this equation has a genus greater than 0. Because in this case, these operators generate commutative subalgebra, which is not generated just by one operator. It's not rational, and it is interesting. Well, in any case, this implication holds only in this case for g greater than 1. Genus is 0 is not interesting case. Well, at this point, I think I can finish this survey of questions related to theory of commuting operators. And later I can develop this survey talk in many directions. First of all, I'd like to say that I'm supposed to give a list of interesting examples, explicit examples of commuting differential operators, not only in dimension 1, but also in dimension 2, and so on. There is a deep theory of quantum completely integrable Cavalera-Moser systems. This theory is also very deep. Many papers are written about that. but I need time to explain everything. This is just a beginning of a series of talks devoted to questions behind that. So today I formulated several most important questions. First of all, the problem of classification of commutative subalgebra in the ring of differential operators. We can consider them as quantum completely integrable systems. Second, the problem of finding explicit examples of such commutative operators. And third, the circle of questions connected to the famous open conjectures like Dychmear conjectures and Jacobian conjectures.
So in some sense, finding commutative subalgebras in, for instance, Fedosov's quantization will give us commutative families of differential operators.
Yeah,
and
exactly.
Probably give us more examples to understand.
Exactly. To find non-trivial examples in A1, examples of commuting differential operators, is not a trivial task at all. Yes. And it's very interesting. The first examples of this commuting of such commuting operators were given by Dychmear in the same paper, 1968. But later examples were produced only in our century, I think. The most interesting examples were given by Andrei Mironov, who gave a solution to one question of Israel Gilfand, to Oleg Mokhov, and then several examples were found by us with Igor Bourbon in our paper. So, well, there are many, and by many pupils of Andrei Mironov. It's an interesting activity. There are many questions. I need time to explain everything. So, okay. Are there any questions? I think that no.
Okay, in this case, we just stop the broadcast.
Yeah.
Say goodbye.
Yeah, goodbye.
And you should please turn off.
Just end.
Yeah, okay, end the meeting. Okay, and go to
Да. Да. Нет, достаточно найти хотя бы одну такую кривую. Одну. Мы, когда стали думать над этой гипотезой, мы с Мироновым, у нас было несколько статей, где мы, вообще-то ее опровергли. Как правильно, мы построили примеры кривых, когда это не так. Но, то есть, когда пространство орбит, пространство орбит бесконечно. Но, на самом деле, Dychmear следует из хотя бы одного примера, то есть хотя бы один пример найти, в котором это дело выполнялось бы, то тогда Dychmear был бы уверен. Но как найти этот пример, совершенно непонятно. То есть, скорее всего, гипотеза Береста неверна, и для любой кривой пространство орбит бесконечно. Но доказать мы это тоже не можем. То есть вопрос открыт. Во всяком случае, вопрос интересный, забавный и, так сказать, перспективный, если на него есть положительный ответ. Вот. Тут, как говорится, то есть, скорее всего, все-таки она в общем случае неверна, но как-то доказать непонятно. Нет, в случае рода единицы она, конечно, верна, тут пространство бесконечно. Но это как бы неинтересно. Но как доказать это для общей кривой, верно это или нет, до сих пор вопрос открытый. Потом, дело в том, что это вопрос чисто алгебраический, то есть поле К можно брать любым полем характеристики 0. В частности, вопрос открыт, то есть наши контрпримеры с Мироновым не работают.